In 2005, he moved to Turin, where he earned his master's degree in telecommunications engineering. For his master's thesis, he combined his studies of engineering and music to explore the musician perceptions of acoustics and the correlation with objective index from ISO 3382. He earned his PhD in metrology, studying acoustics with particular attention to the uncertainty of measurements and statistical analysis of data. He described the concept of speech intelligibility in the classroom and how the acoustical features of a classroom can influence vocal performance. He's also interested in the professional voice user and singer techniques, as well as the definition and quantification of vocal load. So other things that he's interested in are speech intelligibility, room acoustics, and musical acoustics. When he was not doing that, he was a professional chorister and performed under a variety of very prestigious directors. And you can actually look online. He has many publications on the effects of voice style, noise level, and acoustic feedback on objective and subjective voice evaluations. And tonight he is going to be talking about vocal effort in speech, accommodation to room acoustic conditions. So without further ado, let's welcome Pasquale.
Thank you. So, what I was telling is the work that we are doing here with Professor Hunter and with Simon Gretzer, it's mainly related to understand which are the strategies that speakers are using in relationship with the acoustics of the environment and the ambient noise. So, first of all, when a person is interacting with an environment and also with the destination of use of that environment, these three interactions are creating the concept of the acoustic comfort. The maximization of the vocal load, and the maximization of the vocal comfort and the control, and the minimization of the vocal fatigue and effort should be considered, especially when the speaker is at high risk of vocal injury, such as in teaching environment, where the classroom acoustics are particularly poor. So the two goals that need to be achieved in an environment devoted for the communication is the lowering of the background noise and to have an appropriate reverberation time. Just we come back and we talk about what is the sound. We know that when a body is vibrating, it's propagating in the medium, which is an elastic medium, a variation of pressure. And if this variation of pressure is in the frequency between 20 and 20,000 Hertz, it's perceived by human. This is the sound. How we can characterize the sound? So the main characteristic of a sound are the periods, which is the duration of, in the time of one cycle in the sound wave, the frequency, which is the number of occurrences that are repeating in a unit of time, the wavelength, that is basically the same measurement of the periods but not in the time, instead in the space, and the speed of sound, which is connecting these two quantity, the period and the wavelength, and is telling us basically how our sound is moving in a medium. The most simple sound is defined pure tone, and basically it is only one pure sinusoid, which in the domain of the frequency here is it translated as only a frequency. A pure sinusoid, which is the base, the smallest component of a more complex sound, is only one frequency. If I'm adding together more sinusoid, which are the entire multiple of the other one, I'm adding a complex sound, which in the spectrum, in the domain of the frequency, will be a component, will be composed by the three frequencies that are composing that sound. Which is the main difference between a sound and a noise? What do you think about which could be this difference? Some idea? Which is the main thing that comes in our mind when we are thinking about a noise? And
chaos,
chaos, or
indistinguishable tones, you can't really hear a particular.
exactly, this is another idea, the most simple one.
Static.
is
Static, like, on,
a noise can also be not static, if you're meaning. The main one,
oh,
how you can say this is a sound or this is a noise.
If it sounds good.
Exactly. So the main characteristic of the noise is the unpleasantness. We don't like, theoretically, or usually, we don't like noise. Why the noise is not, no one likes noise usually. The reason is related with the fact that someone was telling, so we are not able to decompose or this kind of signal in periodic component. So basically, this is a type of noise. It should be a white noise. It's the shh that comes. You know exactly, you are electronic, so you know. Theoretically, this type of noise is composed by all the frequency. So of course, if I have all the frequency, I'm not able to distinguish any one of them. How I can measure the sound? The main characteristic, the principal way to measure the sound is the sound pressure level. I can measure the sound measuring pressure, and the relationship that is relating the pressure in a point, which is exactly not really the pressure, but is the root mean square of the pressure, is this formula, where P0 is the pressure of reference and is equal to 20 micropascal. What happens when an energy, sound energy, is going against or is impacting with a surface? If I am in an enclosed space, when an energy is impacting through a surface, which is the W, the total energy, it will be decomposed in three parts. Part of this energy will be reflected into the room. Part of this energy will be absorbed by the wall or by the surface, and part of this energy will be transmitted over. There are these coefficients that are called R, which is the reflection coefficient, the absorbent coefficient, and the transmission coefficient, which are giving a percentage of the energy that is reflected, absorbed, and transmitted. And of course, the sum of these three index should be 1, because we can only transform energy. Generically, when we are talking about room acoustics, we are not interested in the transmission component, because this is another part of the acoustics. So when we are talking about inside a room, the acoustic of inside a room, we are combining together the absorbent coefficient with the transmission coefficient, because we are not interested in what is happening outside our room. An example, if I have an opening, so a window that is open, that surface will be associated with an apparent absorbent coefficient equal to 1. All the energy will be transmitted over the windows because it's open, it's an opening. If I have a reflective material, such as a glass, I have an absorbent coefficient of 0.05, which means that the biggest part of the energy, in particular the 95% of the energy, will be reflected by the glass and will come back in my room. If I have a porous material, such as this panel that we have on the ceiling, I have an absorbent coefficient of 0.65, which means that 65% of the energy will be absorbed or transmitted, and 35% of the energy will come back in the room. How I can evaluate the acoustical characteristics of a room? The main tool that we have is the impulse response, exactly as it works for an electronic component or a telecommunication channel. We are exciting our room with an impulse and recording the impulse in a position. We will have the impulse response of that room. If I have a pure impulse, as you know, I should have an infinite energy in infinitesimal duration, but in the path of the sound will be, this impulse will be colored by the environment. I will have multiple reflection and other component of the sound that will change my impulse and will transform my impulse in my impulse response. And in that signal, I have all the information that I need to characterize my room, the acoustical feature of my room. So for example, if I'm considering an impulse that is starting from the loudspeaker arriving to the person, I will have the red flag, which is the direct path, which has the biggest quantity of the energy, is the maximum of the energy that I can obtain. After that, I will have the green, which is a simple reflection, that as you can see will arrive late in the time, because the path that is doing it's longer, and it will be also smaller as amplitude. Why? Because in this point, I will have part of the energy that will go out from the room, part of the energy that will be absorbed by the surface, and only a part of the energy will be reflected. And of course, longer is the path, more are the reflection, longest it is the path, and lower will be the amplitude of my signal. The reverberation time, it's called T60 traditionally. It was measured for the first time by Sabin, and it represents the time that required for the sound level in a room to decrease by 60 dB after the noise generated by the source stops. It's a conventional number. This 60 dB comes out because Sabin was doing some experiment in his auditorium, his university, and he was able to perceive a decay of 60 dB using organ pipe. So this is the reason because it's called 60. I have a source here which is emitting a sound. The source will stop to emit and I will have a decay. Why I have a decay? Who is causing the decay? Who is causing the fact that I don't have an immediate stop of the recorded sound in a place? What do you think?
The sound bouncing off the...
Exactly. I have all the reflection. Even if I stopped the sound from the source, I have periods of time in which there is still sound in the room, even if it is not more generated, but the energy that was generated by the source is still turning around. And of course, more are the reflection, the number of the reflection, lower will be intensity of this sound that is going around. Till I will have a kind of stop moment when the level of the sound that is still around in the room will be equivalent to the background noise that I have. At that point, I'm not able anymore to distinguish the sound that was generated by that source. I will consider a regression line from my decay. I'm considering a difference of 60 dB, and I'm going to evaluate which is the time that is necessary for the sound in the room to decay of 60 dB after I stopped my source. This is a number in second. As you can see, it is evaluated over the axis of the time. And it is really important because the reverberation time is the, I think, is the most common evaluator for the acoustical characteristic of a room. Just to give you some idea of some number, I don't know if you are familiar with this parameter. Generically, in a classroom, the reverberation time should be something about 0.4, 0.6 seconds. If I'm going in a church, in a big church, for example, I can have 13, 14 seconds of reverberation time. In an environment like this one, I think we will have something about 0.8 seconds of reverberation time, and because the relationship, the reverberation time, it depends also by the volume of the environment. Another evaluator for the quality of the acoustic of an environment, it's called clarity. It's called C50, and it's called clarity, and it can be C50 if we are talking about speech propagation, or C80 if you're talking about music. The difference in this number only depends by what we consider as positive sound and what we consider as a negative sound component. If I have an impulse response like this one, the C50 consider as a positive or constructive component of the sound the first 50 milliseconds of the impulse response, and is relating the energy that is in this part of the sound with the energy that there is in the late reflection, which are considered negative, because if you consider speech to speak in an environment with a high reverberation room, there is a kind of superposition of all the syllables that I'm pronouncing. The intelligibility of the words will be less high. And for the music, we are considering a longer periods as good sound, because generically 80 milliseconds is considered that time in which we are feeling ourselves enveloped by the music. It's considered positive to have a longer energy. There are two standards that are mainly talking about the acoustical parameter of a room. The first one is the ISO 3381, which are giving all the information about the measurement of the reverberation time, and in particular there is an Annex A, where are all the measurement to characterize the acoustic of big room or performance room. Another important standard for our work is the ISO 9921, that is an ergonomics standard for the speech communication. What we are mainly interested from this standard is the definition of vocal effort. In this standard, there is a quantification of the vocal effort, which is a psychological magnitudo, but it can be quantified by means of the sound pressure level measured at 1 meter from the speakers in an anechoic situation, so without reflection. In particular, there are some reference, some attributes are given and related to the sound pressure level. We know that a person that is talking very loud as effort will generate a sound at 1 meter of distance with 78 dBA, and loud 72, raised 66, normal 60, and relaxed 54. Do you know the difference between dBA and dBA? Okay, there is just a bit longer. There is this, the dBA, it means when I have an A, in this case there is not, but it's written here. When I have an A at the end of dB, it means that that value was weighted using a particular weighting curves that is based on the sensitivity of the ear. So in the 60s, there were a couple of researchers and they did an experiment testing how people are perceiving the sound using as a stimuli some pure tones at different frequency. And so basically they created a family of curves that are called isophonic curves. And on these curves there is the relationship, in this family of curves, there is the relationship between the sound pressure level, the frequency, and the perception of the intensity of the sound. They are called phonic. And from this audiogram, it's called, taking into account the curves of the 60 dB, 60 phon, it was created a list of weight to add to the real measured sound pressure level in order to better match the measurement of the sound pressure level and the perception of the sound pressure level. And basically in all the environmental engineering, the measurement should be given in dBA, because all the reference value are given in dBA. Something that is really important for our research. What is the vocal load? The vocal load is the amount of speech that a person is doing, and how I can measure this in different way. We are using, or one way to measure it is to use something called vocal doses that are basically an evaluation of different parameter of the speech, such as the sound pressure level, of the fundamental frequency of the speech, and to measure this quantity over the time. So the idea of vocal load is to consider the amount of the speech performed by subjects over the time. And what is the effort? Vocal effort, we said it before, is a psychological entity that accounts for changing in voice production when loading increase, and it can be quantified by means of sound pressure level at 1 meter from the mouth. What is the vocal comfort? Is a psychological entity of which the magnitude is determined by those aspects that reduce the vocal effort. So the idea is to increase the comfort, and which is the control, is the capacity to self-regulate vocal behavior. There can be some pressure level, which is the volume that I'm using while I'm speaking, or the resonance, which means the color of my voice, or other psychological entity. This is the first experiment that one of the first experiments that we did here in MSU. I don't know if you know, but in Michigan State University there is an anechoic room that you can see in the figure. And this experiment was about the effects of speech style, room acoustics, and vocal fatigue on vocal effort. We had two main research questions, and the idea it is possible to decrease speakers' vocal effort by increasing the external auditory feedback. The second question was, if there is such an effect, how does it interact with reverberation time and speech style effects? This experiment is coming from, this idea is coming from my background. During my PhD, as the introductor told, I worked in speech intelligibility and vocal load evaluation in real classroom. One of the problems that came out was that acoustical features that are optimized for the students are giving some value of reverberation time in a room, which are extremely low, as I told you before, 0.4 seconds. And this value seems to be not enough for teacher. So what is happening is that often teachers are complaining to not have enough support from the room. If I am in an environment really dry, as reverberation time, I'm not able to, I don't have enough reflection that are coming back to my ear. So I cannot perceive myself really well, which automatically are leading to an increase of my voice. Because I use my voice self-regulating based on what I'm able to hear. The idea of this experiment was, there's a way to modify the acoustic of the environment in order to increase the performance for the speakers, which are the teachers in this case, without modifying the reverberation time, which is necessarily, it has to be low for the performance of the students, because if the reverberation time is high, there will be an effect on the speech intelligibility. So we used 20 subjects, 10 male and 10 female, normal speech and hearing, no smoking. Our equipment was PC connected to a soundboard, and we used a directional loudspeaker to emit some babble noise in the environment. And we use a microphone, an omnidirectional microphone, a measurement microphone, and also an head-mounted microphone. The rooms that we used were with three different reverberation time, an anechoic room, and what we call the semi-reverberant room, which is a kind of normal room, and a reverberant room, which is the opposite of the anechoic. So it's an environment with really high reverberation time. We asked the subject to read a text with two different voice style, normal and loud. And we changed the external auditory feedback, which means the quantity of sound that was coming back to them, using some reflective panel, plexiglass reflective panel, placed at 50 centimeters from the subject's mouth and 45 degrees according to the frontal axis of the subject. We used in all the experiment babble noise from a classroom, and with a level of 61 dBA, which is a level reported in the literature as a typical noise in a classroom with students that are working in a small group. And we adjusted the volume of the loudspeaker in order to have the same level of 61 in the position of the speakers. After each task, so the task were, as I told you, 3 rooms per 2 styles, which means 6 per 2 conditions of external auditory feedback, which are 12 conditions. Each subject repeated this text, this reading 12 times, and after each repetition we ask them to answer on a visual analog scale from not at all to extremely, to express an opinion about the effort, how effortful was to speak in this condition, how the control, how well were you able to control your voice in this condition, the comfort, how comfortable was it to speak in this condition, and the clarity, how clearly did you perceive your own voice in this condition. Evaluation of the reverberation time in the 3 rooms is reported in this graph. The red one is the anechoic chamber. Labels are totally different. As you can see, this one is from 0 to 0.06 seconds. This one going from 0 to 3 seconds. So the reverberation time in the anechoic room was really small, was 0.05 seconds. In the semi-reverberant room was 0.78 seconds, and in the reverberant room was 2.37 seconds, which is not extremely high, but for our purpose it was good enough. We also measured the clarity in order to appreciate the difference introduced by the panel. And in the first graph there is the anechoic room. In the anechoic room is not the best way to evaluate this because everything is extremely high because all the energy is arriving really soon. But in the semi-reverberant and the reverberant room we were able to appreciate the difference. The red line is the clarity when the panel were present, and the blue line is the clarity when the panel were not present. So we were able to increase that frequency that are the most relevant for the speech. For each subject we calculated a mean of the sound pressure level among all the 12 tasks, and then we subtracted this mean value from all the value of the time history that we had from each single condition. And after that we ran a model, a linear mix model, considering as response variable delta SPL, which is this SPL centralized per subject, and using as predictor the style, the room, and this particular variable that you can see here, order. I will explain now what is this, and the interaction between room and style, and the interaction between room and order, and also the interaction between style and gender. Why we insert order? As I told you, each subject performed the reading 12 times. Order of the presentation of the task was randomized, but per each subject we keep the order in which the tasks were presented, and we insert this factor in the model. The reason is that we were looking for an effect of short-term fatigue. So basically this order, it's random, so there is not other effect on it. It's only evaluating if there are some changing in the voice with the time. When the style was loud compared to the normal, of course, we had 8.32 dB of increase, which was expected. And there was also a difference between gender. Female used a larger range of variability in the sound pressure level than male. When we introduced the panel, we had a statistically significant reduction of the sound pressure level. It was small, it was 0.5 dB, but it was still significant, so it means that we can improve that. And there was not a difference between gender, so both gender reply in the same way to the presence of the panel. In the 3 room, we had different reaction. In particular, in the loud style, delta SPL decreased as the reverberation time increased. While in the normal style, we had the highest value of vocal effort in the semi-reverberant room. So this kind of behavior is what is reported in the literature, even if it is totally not intuitive. What I'm telling there that if I increase the reverberation time, a person will speak with a lower volume. What I'm telling here is that in the normal environment, which is the semi-reverberant environment, a person will have the highest vocal effort. So these results were not what we were expecting. We knew this because all the papers that are talking, there are not a lot of work about this topic, but all the work that were made on this topic are reporting a similar result, which as I told you, it's also a kind of nonsense because it's not particularly intuitive. We tried to explain the reason, and one of the explanation that we were able to give is this one. Why I use order in my model? As I told you, order can be considered as an evaluator of the fatigue, how I'm changing my vocal effort over the time. In these three graphs, you can see the different behavior that there was in the anechoic, in the semi-reverberant, and the reverberant room. The slope of these three regressions are kind of giving us an evaluation of the rate of the vocal fatigue. How much I am fatigued in a particular environment in relationship with the reverberation time. So as you can see, the reverberant room, I have a fatigue rate that is 0.13. In the reverberant room, I have a rate of 0.2. In the anechoic room, I have a rate of 0.24. Thanks to these results, we were able in such a way to explain our results. Yes, it's true that we have that kind of results considering the overall performance of the subjects, but it's also true that our text was 30 seconds long, so they repeated 12 times 30 seconds. It's not a lot of time for really have an evaluation of which will be the performance in a type of environment. In this way, we were able to predict that if the subjects were talking for longer periods, according with this slope, the semi-reverberant room will be the highest performed room for the speech. The idea was that, yes, it's true that overall, using a normal level in our data, the semi-reverberant room is the one that is giving the highest vocal effort, but it's also true that it's the one that is giving the lowest rate of vocal fatigue, which is important if I have to talk in an environment for many hours. As far as the subjective evaluation, as I told you, after each task we asked about self-perception of the effort, the control, the comfort, and the clarity. Of course, the effort was strongly influenced by the style, so I have 27% higher effort when I'm talking loud, but there is also an effect of the room, and higher is the reverberation time, lower is the perception of the effort, and there was, as we were expecting, also an effect of the panel. So when I'm increasing the external auditory feedback of the subject, there is a decrease of the, more or less the 5% of the effort. As far as the control and the comfort, they were only affected by the style. The control and the comfort of in the use of the own voice was higher in the normal style than in the loud style. The last question was about the clarity, how clear you can perceive your own voice. And the only significant effect was related with the panel. So when we increased the external auditory feedback, there was a higher perception of the clarity of the own speech. As far as results related with the room, as you can see in the loud style, there is the same pattern that there was for the objective evaluation of the vocal effort. In the normal style, there is not a statistical difference between the room. The reason because of this is that we are supposing that in the loud style, when I'm introducing the panel in the reverberant room, I am creating too much reflection. The reflection that are caused by the environment, because the environment is highly reverberated, plus the reflection that are created by the panel are creating a kind of saturation of reflection, which are becoming annoying for the subject. He is considering not enough good. To conclude this experiment, our question were, is it possible to decrease speakers' vocal effort by increasing their external auditory feedback? And the answer is yes. We have been demonstrated that the placement of a reflective surface can improve the quality of the sound field for speakers. The increase in the external auditory feedback due to reflective panel significantly reduce the vocal effort. If there is such an effect, how does it interact with reverberation time and speech style effect? The effect of the panel was consistent in all the room and it was consistent in both the style, but of course it was higher in the loud style, and it was strongest in the reverberant room, followed by the semi-reverberant room and the anechoic room. Another interesting conclusion is related with the fact that different reverberation time are leading to different rate of vocal fatigue. In particular, across the 12 tasks, this rate were 0.13 dB per task for the semi-reverberant room, 0.24 dB per task for the anechoic room, and 0.20 dB per task for the reverberant room. So it could be predicted on the basis of that vocal effort in the reverberant room would have surpassed that in the semi-reverberant room if the subjects had been asked to speak for longer periods. I have another small experiment. We are working in the voice and in the Vibal laboratory across road, and we are doing all these kind of experiments related with voice and room acoustics in this moment. And some of these experiments are really small, and if you are interested, you can contact me, you can come to the lab meeting that we have each Tuesday. And if you are interested in doing by yourself a small project, we are really open to every kind of idea. This project is really small, and it was done by Ivano, which is a student now is working with us as data analyst, and experiment based on a simple idea. There is often, the Lombard effect is an effect really common. When you are in a noisy situation, there is the tendency, subconscious tendency to increase the level of the voice. If I am in a noisy environment, if I'm going to a bar or somewhere else and I'm talking with someone and there is a lot of music or a lot of noise in the environment, often at the end of the night I have sore throat and I don't know why. The reason is that I was shouting and I was not conscious of that because I'm kind of regulated the level of my voice with the background noise. The question of this small experiment was, is there a change point in the level of the noise for the Lombard effect, and how is related with the disturbance of communication and the vocal discomfort self-reported? The procedure was pretty much the same. I will skip and I will go to the results. So this is the main situation. In these first graphs, we have the effect of disturbance with the level of noise. We placed 20 subjects in a soundproof room. We increased the level of a sound source with step of 5 dB, starting from 20 dB, which was the background noise of the soundproof booth, till 65 dBA of pink noise, which is a noise which has the same energy in each octave band. And we asked them to read a text to a person that was in the room with them at 2 meters of distance. After that, we asked them to answer a question about how much they were disturbed by the noise in a scale between 0 and 100, and how much they were discomfort in the use of their own voice between 0 and 100. In this graph, in the center, we have delta SPL exactly as we calculated before, so it's centralized per subject. Blue are male, F are female. There is no difference in the pattern between both of them, but the Lombard effect, basically, it is represented by the slope of this line. Our hypothesis was, we think that there is a starting point, there is a level of noise that is kind of giving the start to this effect. We use a particular statistical package. It's basically performing a segmented linear regression model, and we found that changing point was about between 40 and 45 dBA, which is interesting, which is also something that was in such a way reported in the literature. It was not really well explained, but in the literature it was written that there was not a particular effect of the Lombard effect for noise, level of noise lower than 40 dB. But it was not proved. What is particularly interesting of this experiment, it's the relationship between these three graphs. So it's like that people are starting between 30 and 40 dB to be disturbed by the presence of the noise. After the disturbance it started, they automatically change the level of the voice with a different rate, which is 3 times higher than the one that I had before. And after a while, about 50 dB, they start to feel discomfort because they are using differently their voice. They are increasing the level of the voice. This one is really a small experiment that we did, and we are trying to publish an express letter on the Journal of Acoustical Society of America with this, and this is the kind of work that we do in our lab. The future research that we are going to do soon is to analyze more the effect of reverberation time on vocal fatigue. We are starting to use virtual electronic box that we can use to change in real time the reverberation time and other acoustical parameter. And we want to evaluate how the fatigue will change in different environments using longer periods of time and rating the subjective evaluation of the fatigue more often. Another study that we are doing is the effect of reverberation time on speech intelligibility. So mainly my colleague Simone Gretzer, she's interested in understanding which are the acoustical characteristic of the speech, not considering the level, so all the other characteristics that are creating a higher level of intelligibility of the speech. The third experiment that we are going to do is the effect of side tone level on vocal fatigue. Changing the level artificially, electronically, changing the level that is coming back to my ear, this higher level of noise will act as the Lombard effect, so I will perceive that as noise, or the fact that that higher level is my voice will lead to a decrease of my voice. This is the question. The fact that I'm increasing the level of sound pressure level that there is around me theoretically should act as the Lombard effect, so if I have more noise around, automatically I will increase the voice, my voice level. But if that noise is not noise, but is my own voice, what will happen to my voice? I will increase my level, or I will decrease. So this is called side tone level. Side tone is because from the telephone, so basically it's the voice that is coming back externally to my ear. Thank you. You're welcome.